In the last video, we solved exponential equations that could be reduced to the same base. But what happens if you can't reduce them to the same base? For example, I'm asked to solve 2 to the x power equals 5. Now, 2 and 5 can never be the same base. This is 2 to the first power, 5 to the first power. They're both prime numbers. Can't factor them. There's no way I can make 2 and 5 have the same base. So what do? There's one of two ways that you can solve this. So the first way is take this exponential equation and rewrite it logarithmically. So that just means I'm going to say log of base what? The base is 2. So subscript 2. Of, what does that equal? 5. And this log, base 2 of 5, will equal the exponent. The exponent here is x. Now remember back when we did that change of base formula? So if your calculator doesn't have a button where you can put in different bases, you have to use the change of base formula. So I could leave it as log base 5 of, or divided by, log of 2, right? So log of what you're taking the log of divided by log of the base. The base always goes in the bottom when you're using that change of base formula. This would be the exact solution. So if you're ever asked to leave it exact, you could leave it exact. You could also write it as ln of 5 divided by ln of 2. That's the same thing. But if you're asked to approximate it, we're going to go ahead and type that in our calculator. So I'm going to clear this out and type in 5, take the log of that, divided by 2, take the log of that. That will equal, and I didn't say where to round any of this, so let's just say to the hundredths, 2.32. One says leave it alone, so 2.32 approximately. Just pay attention to where your homework asks you to round it if you are asked to round versus leave it exact. Okay. Now there is another way to do this, and that's using this property here. It says the logarithm property of equality. Let a, b, and c be real numbers such that log base b of a and log base b of c are real numbers, and b is not 1. Then set those two equal to each other is equivalent to a equals c, meaning the stuff inside equals the stuff inside here. And you could take the log of both sides of this equation and then use an exponent property that we haven't learned, but if you've seen it in previous classes, that should get you to the same answer. Alright, let's look at another one. In this example, we have 3 to the 2x minus or plus 1 power equals 8. 3 and 8 will never have the same base. 8 is a power of 2, so 2 cubed would give us 8. So the base would be 2 here versus a base of 3. These can never match. I'm going to rewrite this logarithmically. So log, start with the base. The base is 3. Take the log of what this equals, which is 8. And that will equal the exponent, because logs equal exponents. So 2x plus 1. So now I have to continue to solve for x. X is not quite alone here. So I'm going to use the change of base. This is log of 8 divided by log of 3. And I will subtract 1 from both sides. That equals 2x. And then lastly, we're going to divide by 2. But a problem like this, you would most likely not be asked to leave it in exact form. So I'm just going to go ahead and get this in my calculator and do 8, take the log of it, divided by 3, take the log of that, And when I divide those, I get 1.827. And then we will subtract 1. So I left that whole thing in there. I'm not rounding until the end. And I get this decimal. And then I would divide both sides by 2 after that. So take that answer, divide it by 2. And then depending on where your homework asks you to round that, I'm going to go ahead and round it again to the hundredths. So tenths, hundredths. That 6 says round that 4 up. So this is, x is approximately 0.45. Never rounding until the end. Again, this is the approximate solution because I have rounded. Let's do one more here. Now this example has e to the 2x power equals 12. So when I rewrite this logarithmically, because this is still an exponential, exponentials have variables in the exponents, I can rewrite it logarithmically. I would say log base e of 12 equals, logs equal exponents. So the exponent was 2x. But because this is log base e, this is a special log. This is the natural log. So I'm going to rewrite it as ln of 12 equals 2x. Remember, log base e is the natural log. So this whole thing becomes the natural log of 12. Divide both sides by 2. Again, this would be the exact answer if you're asked to leave it that way. Versus, if I put it in my calculator, I would say 12, take the log, or the natural log of that, divide by 2, and rounding to the hundredths, it's approximately 1.24. Approximately 1.24. Again, pay attention to how you're asked to round that for other homework assignments or tests or things like that. Something important to note is there's a difference between using the change of base formula and just having log base e. Okay, so here I'm changing it, and I can use any base I want. So I could use ln of 8 divided by ln of 3. Down here, this is log base e, which is natural log. I cannot use other logs here. This is natural log. Okay, so keep this change of base separate in your mind from log base e, which is a natural log. Go ahead and try these 3 examples on the right hand side. On the right hand side, I have 3 to the 2x power equals 6. Sometimes students think that they can get these to the same base because 6 is a multiple of 3, but you can't. There's just no way to do it. Right? I would have to have 3 to the first, 3 squared, 3 cubed, which is 3, 9, 27. There is no power of 3 that gives me 6. Okay? So I cannot rewrite these with the same base. I'm going to rewrite it logarithmically. So again, logs and exponentials are inverses of each other. So to undo an exponential, I'm going to rewrite it as a log. To undo logs, I'm going to rewrite it exponentially. That's how we undo them, just like add and subtract, multiply and divide, squares and square roots. We want to undo the process that was done. So I'm going to rewrite this as log base. The base is 3. And I'm taking the log of 6 because 2x has to be what that log equals, because logs equal exponents. Sometimes it's easier to just start with log and then the base, and then what does this log have to equal, which is the 2x. because logs equal exponents, and then put in that last number you haven't used yet. So I'm here. My calculator doesn't have base 3. I'm going to rewrite this using the change of base formula. Log of 6 divided by log of 3 equals 2x. And then I'm going to divide both sides by 2. So this log base 6 divided by log of 3 is going to get divided by 2, and that's going to be x. So let's plug that in our calculator. So 6, take the log of that, divide it by 3, take the log of that. Don't forget to hit equals. So that's 1.6309, and then I'm going to leave this whole long thing in my calculator, divide by 2, and get 0.8154 blah blah blah. So let's go ahead and round this to the hundredths just for the sake of time. Tenths hundredths, 5 says round that up. I'm going to round it to 0.82. So this is approximately 0.82. Next example. I have 5 to the 3x minus 2 power equals 7. 5 and 7 can never have the same base. I'm going to rewrite it logarithmically. I'm going to undo this exponential equation with a logarithm. So log base 5, I'm going to leave some space here, that will equal, well, logs equal exponents, so the exponent is 3x minus 2, and then I have to take the log of something, so I'm going to take the log of 7, the only value I haven't used yet. Now, again, my calculator doesn't have base 5, I have to use a change of base here. So log base 7 divided by log of 5. Log of 7 divided by log of 5. Remember, the base is always the one that goes in the denominator. And then to get x alone, I'm going to add 2 to both sides, equals 3x. And then whatever that answer is, I'm going to end up dividing that whole thing by 3. So you have to evaluate this first and then divide by 3. So that's what I'm going to do in my calculator. I'm going to take 7, take the log of it, divide by 5, take the log of that, figure out what that equals, and then, so I've done this. Now I need to add 2, gives me 3.2, and then lastly, divide both sides by 3. So take that, divide it by 3, and that equals, if I round it to the hundredths, 0, 6, that 9 says to round that up to a 7. So x is approximately 1.07. And in all honesty, you'll probably be asked to take that out farther to 3 decimals or 4 decimal places. So don't think that this is always going to be the hundredths. That's just what I chose to round these to. Last one says e to the 5x power equals 9. Again, e is 2.7 approximately. Can never have the same base as 9. I'm going to undo this with a log. So I rewrite it as log, the base is e. That will equal, logs equal exponents. The exponent is 5x. And log base e of 9, the only value I haven't used yet. Now remember, log base e is the same thing as the natural log of 9. Sometimes students just go directly to that step, knowing that because it's base e, it's going to be a natural log. I'm just filling this in so you can see the process of how it's going from a log to that natural log. And then lastly, to undo this multiplication, we divide by 5. So ln of 9 divided by 5 equals x. That is the exact answer. and then approximately, I plug it in my calculator. 9, take the natural log of that, and then divide by 5 equals approximately out to the hundredths. Look to the right. That 9 says round up, so x is approximately 0.44. Again, I'm just trying to stress the difference between an exact answer versus an approximate is one that you have rounded.